Hi guys, before we go into organic chemistry reactions, it's good to do a little bit of review of Gen Chem, particularly thermodynamics and kinetics, which will help us understand the driving force behind reactions. Why is it that they occur in a way that's product driven, and then also the kinetics of a reaction, which is how fast is the reaction, how do we get a reaction go faster. And then the second part of this video will be on carbocations. So we'll start with this Gibbs-Helmholtz law here. It's a very familiar law from Gen Chem. Delta G is Gibbs free energy, and I think of it as just spontaneity. How spontaneous is a reaction? How likely is it to go forward as opposed to in the reverse? We know that a negative delta G is a favorable reaction, meaning a reaction drives forward with negative delta G. If we have a positive delta G, that's less non-spontaneous, so we're likely to have no reaction or reactant favored situation. Now, there are three factors which affect delta G. The first one is enthalpy. So enthalpy I think of simply as the heat of a reaction. You may remember doing Hess's law or heats of formation or bond dissociation calculations, and you've got negative enthalpy change is going to be exothermic, and exothermic reactions tend to drive the delta G to be negative, which means it tends to drive reactions to being more spontaneous, so more product driven, as opposed to endothermic, which will be positive delta H, tends to lead to positive delta G, non-spontaneous reactions. But it doesn't necessarily mean it has to be that way, because we have these terms as well which can influence spontaneity. So we have temperature and we have something called entropy. And many people just think of entropy as disorder. If I start with one molecule and it dissociates, I've increased the entropy of the system. So another way to think of it, though, is it's all the ways you can distribute energy. So the many ways you can distribute energy, you can do more distribution of energy when you have more particles, for example. So entropy tends to be positive when you increase the number of ways energy can be distributed, or when you have more disorder. So you tend to want to go toward a positive delta S in order to have a negative term which contributes to a negative delta G, which is then more spontaneous. So these are the signs that you would hope to have for spontaneity, although the temperature term can really affect that as well. The temperature would be really crucial when you have delta H, which is positive, and in order to have a large negative free energy, you'd need delta T to be large to make this negative term larger. So the temperature can help make the entropy a larger or a smaller factor in determining your delta G. So the temperature can help a lot with determining the spontaneity. So down here I have two reaction diagrams, one for an exergonic reaction, that's where you have the free energy change that is negative, and an endergonic where you have a free energy change that's positive. I also want to note that sometimes we just label the y-axis potential energy or simply energy, and then the terms that we use for exergonic, actually we tend to use delta H then, which is negative when it's exothermic. So exergonic is used when we're talking specifically about delta G. Exothermic is generally used because often the entropy of a reaction may not be the main driving force. Particularly with organic chemistry, you don't have necessarily a big entropic change. For example, you might start with two molecules, and when you react them, you end up with two molecules. So without phase changes or anything like that, your entropy is going to not be very different. So oftentimes in organic chemistry, we tend to have a delta G that can be predicted by delta H alone. So delta H is often used, and you always hear exothermic, endothermic in chemistry, right? But it is important to note when it is important to talk about delta G, and I think you see that more in biology especially, because you don't always just consider bond dissociation or things like that. You want to look at the overall reaction in terms of delta S as well. Here as well, you have potential energy when it's a positive change. We say that's a positive enthalpy change, which is endothermic instead of endergonic. But in either case, we're talking about a net overall gain or loss of energy. So I'll give you an example in biology where we use the term exergonic a lot, which is the hydrolysis of ATP. So it's the energy molecule that our bodies use, and they're coupled to processes that require energy. ATP sort of is the source for some misconceptions, because if you think of ATP and a phosphorus breaking off of it to make ADP, usually you think energy is released, but actually with ATP to break bonds, it takes energy. That's an endothermic process to break bonds. It actually takes energy in to break a bond. So how is this reaction overall exergonic then? Well, even though it takes energy to break this bond, you're forming products that are more stable than what you're starting with in terms of free energy. So even though the process of breaking this bond is a positive delta H, you're also creating products that are more stable at the end, which means you're going to have a net release of energy. And then that's the energy that can be coupled to endergonic processes such as phosphorylation of glucose or other metabolic processes. So we saw with thermodynamics that we're answering the question about whether we have a product-favored or reactant-favored reaction, but it doesn't tell us how fast that reaction occurs. That has more to do with the field of kinetics. With kinetics, we learned how to write rate laws, how to make relationships between the rate of a reaction, or how fast the reaction is, with the concentration of its reactants. So in Gen Chem, you probably wrote out a lot of rate laws. A rate law is an equation that tells you how to calculate the rate. The rate of reaction is equal to a rate constant, which is a number that allows the rate to be related to concentration of the reactants, which goes back to collision theory. So if you have molecules and you have a more concentrated solution, they're going to collide with each other more, and a greater concentration can then give you a greater rate or faster reaction. Some of them change proportionally, and that's first order, meaning the exponent is 1. Some reactions might involve two reactants, A and B, and if it increases with respect to A to the first power and B to the first power, then the overall rate order is 2. 1 plus 1 is 2, so we call this a second order reaction, even though it's first order with respect to A and first order with respect to B. Or you might see in Gen Chem sometimes that it's one reactant, but it's to the order of 2. We generally, with organic chemistry, see reactions that involve 1 or 2 reactants. So if it's one reactant that affects the rate, we call it first order or unimolecular. It depends on one of the reactants. And then the concentration of both reactants, when that affects the rate, we call it a bimolecular. And then third order is just a demonstration that doesn't always have to be 1-to-1. But I'm going to say pretty much we're going to be focusing on first and second order for now. So here's some energy diagrams again, and notice we've got potential energy here. And when we think about the thermodynamics of this process, we're comparing the starting and ending energy, and you see that there's a net release. And potential energy means I'm going to speak in terms of delta H, and I'm going to call this exothermic. Here as well, I have an overall negative delta H. So notice both of these are about the same negative delta H, so they're about the same exothermicity, but this is a faster reaction and this is a slower one. And you can see the reason why has to do with this activation energy barrier. So for example, think of this as a hill, and so you've got a shorter hill to climb. So in terms of getting this reaction started, it takes less energy than over here. It's a much larger hill to climb. Is going to be slower to climb a big hill. So I think of a match. You know, a match, you need to strike it in order to get that combustion reaction started. So I think of that initial amount of energy as that activation energy that's required to get a reaction to occur. So for these energy diagrams, you have A plus B reactant molecules, and let's say that there are two possible pathways. One is to make products E and F, and the other is to make products C and D. My question for you is, which one is thermodynamically favorable, meaning which one will be more exergonic or more spontaneous? And then the other question for you is which process will be faster, making E and F or making C and D? And for now, since this is potential energy, let's go ahead and say delta H is approximately delta G. And let's do that for both of these. Answer the question, which is thermodynamically more favorable and which one is more kinetically favorable? Go ahead and think about that for a minute. Okay guys, so we see on the left that this pathway produces a more stable product. So we're going to have a greater negative delta H than for making E and F. So this is also an exothermic, or let's say exergonic if delta H is approximately the same as delta G. And so they're both exothermic, but this one's more exothermic. So we would say making C plus D is going to be thermodynamically driven. And then in terms of which reaction's faster, I would look at the activation energy. So for this process down here, this is the activation energy, or delta E A, versus the other one, which is up here, so delta EA. So this is also not only the thermodynamically favored, but the kinetically favored, or faster reaction. And then for this process, let's do the same thing. We see that making C and D is going to be more thermodynamically favored because these products are more stable than the reactant compared to E and F. But we see that E and F have a smaller hill to climb. So smaller activation energy means that making E and F is going to be faster. So you might ask, well, which one is more important, thermodynamic or kinetics, in terms of determining which reaction is more likely? So I would say this is where temperature comes in. So look at the activation energies. If you have a system that is at lower temperature, so you don't have as much energy to use for activation barrier, you're probably going to be more likely to go this route because you only have a little bit of energy available. But if you heat up the system and now you have more energy available, you might be able to overcome this hill. You might also learn in subsequent classes that when you have a lot of energy available, the reactions can also tend to reverse. And so we sometimes also look at the reverse activation energy. C plus D has to go all the way up here to get back to A and B. So we would say C plus D is less reversible than E plus F. It's a lot easier for E plus F to go into A plus B and go back and forth like that. So E plus F definitely looks more reversible. So that's a consideration as well when you look at reactions later on. So particularly in organic chemistry, we're going to start seeing reactions that are multiple steps. And this is what a reaction diagram might look like with multiple steps. So think about having a molecule, and maybe the first step might be dissociation. And now that you have these pieces, they might be high energy. So I'm going from here to this process of breaking bonds and having intermediates, which are not my final product. So these can then undergo subsequent reactions, maybe with another molecule, and you might have this kind of situation. So here's something different now. So we went through another step, and then maybe this breaks off, and then maybe this comes back on like that. And so you've got these multiple things happening one after another. So here's my first step, and then I make intermediates, which then can react. So they're sort of like the products of the first step, but are used in directly in a next step to get more intermediates, and then these intermediates go to the final product. So you've got these different intermediates that can be different energies, and I think you'll see a lot of times they're higher energy and then they sort of get lower and lower in energy, but it just depends on the reaction. And then you also see these transition states, and that's the structure of the molecule as it's breaking and forming bonds. So we'll see that soon. But these are very high energy. So if you look at step 1, the highest energy point is actually a transition state, and then the intermediate is sort of a local well that is a minima that happens, it's the lowest point in this area. And then once you have a little more energy, you can get to the next transition state, which then leads you to a different local minimum. And you can keep going until you finally reach the lowest energy state out here. Now, intermediates can be reacted and trapped, and there are ways to detect the intermediates. But with transition states, they're a lot more elusive. You can't stop the reaction here at the highest point. So the transition state is exactly that. It's a state at which it's undergoing transition, which is impossible to stop. So my analogy for this is Teen Wolf. I don't know if you've ever watched that. I am sort of referring to the 80s version with Michael J. Fox, but I know there's some remakes out there. So think about Michael J. Fox as a teenage boy, and here he is starting to turn into Teen Wolf. He's got the fangs growing in, the facial hair and the ears, and his chest hair, and it's just going crazy. You can't stop him as he's transitioning into a wolf, and here he is as Teen Wolf, right? And so it's and I guess at that point that would be more like a product, and then he could reverse back into reactants. But that transition state is that very high energy. He's right in between being a boy and a wolf. If instead Michael J. Fox turned into, let's say, he had the fangs first, and he's walking around with fangs, and then he's walking around with the ears, and then he's walking around with the facial hair, that would be more like stepwise. That would be more like he is undergoing these steps. He's got these intermediates working him through to finally being Teen Wolf. So that's going to be much different. So intermediates tend to be molecular species that step you through to the final product. This here is an example then of a 3-step reaction. You've got step 1 here, step 2, and then step 3. And each of these steps has an activation energy. Let's go ahead and mark that. I'm going to ask you which of these is the largest. I think it's obvious it's this one. And so this will be my slowest step, which is also called my rate determining step. So in terms of kinetics, you probably remember the rate determining step is the bottleneck of the reaction. Oftentimes the rate of this whole thing will depend on how fast this part can be. So here's an example of what a transition state might look like. So again, we can't isolate the transition state, so it's just sort of our best prediction of what the molecule looks like when it's transitioning from reactants to products. So here's the highest point on the energy diagram. That's the transition state. It is a picture of the bonds breaking and forming in a reaction. So here we have a methyl bromide and we have a chloride. And look at what's happening. The chloride is replacing the bromide. Okay? So obviously the bromide has to come off and the chloride has to come on. So here's the bromide coming off, so it's breaking away, and here's the chloride coming in and forming a bond. So they both look the same in terms of the dots. The dotted line means that we're breaking or forming bonds. So this in itself is not a molecule. This is just the way that we think of this process happening. And then here's another one where we have a two-step reaction. And which step is the rate determining step? I think you guys see this one has a larger activation energy, so the rate of this overall reaction is going to depend a lot on this first step. Here what's going on is the bromide is coming off, and we get a carbocation, which we'll learn about more in the next session. And then the chloride comes on, and we make this molecule. So what's happening here is we get an intermediate, which is this carbocation, which later we can react to see as a chloride being attached here. And there are ways that we can know that this exists. So this, the transition state here, what would that look like? The easiest thing is to just identify what bonds would have to break and what bonds would have to form to make this intermediate. Notice the intermediate is just the carbons separated from the bromide. So basically, taking this bond and breaking it. So to draw the transition state, I'm going to draw this, and then dot, 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 dot to show the bond breaking. And notice that the electrons are going to go with the bromine to become bromide. So this is going to start developing negative charge. And then this is losing electrons, so it's going to start developing positive charge. So that's sort of nice to have on there as well. And then we always put the transition state in brackets with a double dagger, as opposed to brackets for the intermediate with no double dagger. Now let's also draw the transition state for the second process. Why don't you guys go ahead and try that one? So for this second one, I would say that what's going on here is this carbon group is attaching to this chloride ion. These two are getting together, and we're forming a bond. We're forming this bond here. So what I want to do is show that bond forming between a chloride and the positive charge of this carbocation. So I'm going to show this is partially positive and this is partially negative as they come together. So down here is an example of how to think of the transition state. Is it right in the middle between reactants and products? I would say normally not. Normally we think of the transition state, which is, again, something we don't see. We can't see it, but we try to use that concept to help us understand what's going on in the reaction. And normally you'll see that it's actually skewed, that the transition state tends to be closer to the reactants or it's closer to the products. And so when you see that it's closer to the reactants, it's usually because its energy is closer to the energy of the reactants. So we call this an early transition state because it's closer in energy to the reactants, which means that we're assuming it's close in structure as well. It's some kind of a structure that resembles the reactants more than it resembles the products. For example, over here, our transition state is closer to the reactants in energy than it is to the products. So we're saying that the bromine might be closer than the chloride in this case, just because it's going to resemble this more than it's going to resemble that. In terms of an endothermic process, now we've got a product energy is closer in energy to the transition state. So this transition state gets shifted a little bit closer to the products. So that's what we call a late transition state. And this is based on something called the Hammond Postulate. I would just simply say the structure and energy of the transition state resembles the species closer to it in energy. And so that's going to be based on whether the reaction is exothermic, it's going to be closer to the reactants, versus endothermic, it's going to be closer to the products. An important consequence of the Hammond postulate is something very useful. It's an application of the postulate that I like to use a lot, which is that, let's say that we have a reaction. I'll just build off of this one. Let's say we have a reaction that's multiple steps, and we've got one intermediate. Let's call this an intermediate here. Intermediate. And let's say that in purple, I have an intermediate with a certain energy here. And let's say that there's another reaction where the intermediate might be higher in energy, like here. Then I can sort of use the Hammond postulate and say, well, the energy of the intermediate is going to resemble this transition state here. So if this intermediate's lower in energy and this intermediate's higher in energy, then this transition state will have a higher energy than the transition state of the first process, which has a lower intermediate energy. So once more, if you have two processes, one leads to a lower energy intermediate, then its transition state will have a lower energy as well, because they should resemble each other. Therefore, the overall, we've got an activation energy for this process that will be lower in energy than the activation energy of this one, because of this energy difference between the intermediates. If you didn't get all that right now, it's okay. We're going to do that again later. So, but it's just a good idea to hear a few times. So what it does is it helps us to predict, based on the differences in energy of the intermediates, which reaction pathway is going to be faster. So it tends to be that the lower energy will be faster. It's not always true, but it's an assumption that we can make in some cases. So in the last part of this clip, I want to talk a little bit about some new vocabulary. So old vocabulary is acid and base. We tend to think of the Bronsted-Lowry definitions of acid and base, which are that an acid is an H plus donor and a base is an H plus acceptor. And when we think of our typical acid-base reaction, like HCl and NaOH make H2O and NaCl, when you look at just really basic acid-base reactions like this, they're driven by thermodynamics. Like, you know that this delta G of this reaction, or you know the K value is very large. You know that this is virtually irreversible. It's very hard to take salt water and make it back into HCl and NaOH. So you've got a very negative delta G. Whenever we talk about acids and bases, we usually talk about the spontaneity or the K value. So we think about HCl dissociating into H plus and Cl minus as having a very large K value, because HCl is a strong acid. But we don't usually talk about how fast this reaction is. So when we talk about kinetics, we usually use different terms. We usually use the term nucleophile and electrophile instead of acid and base. Now, it turns out that nucleophile is a type of base. It's maybe a base that you really haven't used much up until now. So this is called a Lewis base, and it's thought of as an electron donor. And an electrophile is the opposite. It's a Lewis acid, which is an electron pair acceptor. So on one level, these are acids and bases. Nucleophile comes from, phile means to love, and nucleus is nucleo. So this is a nucleus lover. A nucleus is positive, so a nucleus lover is negative. And that's why it has the symbol Nu for nucleophile with a lone pair and a negative charge. So that's how we think of as a Lewis base as an electron pair donor. It's got an electron pair to share. Electrophile comes from electron lover. So if you're an electron lover, you must be positive. And that's why the symbol is E+. I recommend you use these symbols a lot because that's going to help you. You can I think you can say organic chemistry is all about nucleophiles and electrophiles. It's basically all Lewis acid-base chemistry. So some common Lewis bases are any kind of base here. So like a Lewis base can be hydroxide, a Lewis base can be ammonia. So the same type of Bronsted-Lowry acid bases we had before. But you might also see things like aluminum tetrachloride like that. Or you might start to see carbon anions like this. Okay, so these are going to be electron pair donors. And then electron acceptors are going to be the same types of things we saw before, so H plus certainly, but you can also get things like AlCl3 or BH3 or any kind of molecules which can accept an electron pair. Now, what does this have to do with kinetics? I would say that nucleophilicity is not always the same as basicity, and I'll give you a key example. A few weeks back when we did acid-base chemistry, we were looking at the strength of various bases. And what we were talking about was how electron-rich the cloud of electrons was on these oxygens. So oxygen is electronegative. It pulls the density of electrons toward itself. The more carbon groups you have, the more electron density you can have on the O. Okay, so here I've got the most carbons in this tert butoxide, so it's pulling the electrons toward the O. Here it's got a chain of carbons, it can pull the electrons toward the O. Here it's only got a hydrogen, so it has the least dense. So I would say by induction we have a stronger base on the left here. Tert butoxide is the strongest base compared to the others by induction. So we learned that before. Now what I'm going to say is, as a nucleophile, how well do these bond to something else? A complicated molecule here, like many atoms, and it has a little spot here for reaction. So if I'm this big complicated molecule and I want to bind to one of these, which one's going to be the most effective? Well, I think you know the hydroxide is going to be able to fit a lot faster and perhaps make a faster bond because it doesn't have the repulsion from all these carbon groups affecting how well it can bind. So in that sense, hydroxide's going to be faster than the others, even though these might be more electron rich. So the size factor and steric repulsion then leads us to say hydroxide is a better nucleophile, even though it is a weaker base. And therefore, we tend to use these terms more in referring to the kinetics and which species are going to be faster, not just the most basic or most acidic.